Good afternoon, everyone. So it's my pleasure to introduce Mary. And Mary is a scientist 3 she has a joint appointment between the ACOM, formerly known as ACD, and M-Cube. And she received her BS in chemical engineering from CU here in Boulder, and then she got her PhD from the University of Washington in atmospheric sciences in '91. She came to NCAR as a postdoc, and then with a joint appointment, and then she had a joint appointment with M-Cube and ACD and has worked at NCAR ever since. She's currently a group leader on the regional and process modeling group and the NCAR WRF-Chem development lead. And over the course of her career, Mary's research has focused on interactions between cloud and chemistry, and this is really going to be the focus of her talk. And really going through some really important work on identifying chemistry, the impact of aqueous-phase chemistry, cloud scattering on ozone chemistry, but also sulfate aerosol loading in the troposphere. And so the results of all this work, and this will be discussed, I believe, very clearly in Mary's talk, is the DC3 field campaign of which she was a PI. And then over the last few years, Mary has also led an NSF-funded Earth system modeling project on chemistry and climate in Asia, focusing on applying WRF-Chem to South Asia and Southeast Asia for a variety of studies. So with this, I'd like to welcome Mary.
Thank you, Jean-Francois. I'd like to begin by acknowledging all the people who have collaborated with me in looking at clouds and chemistry. Many of those people are listed here. In particular, I want to thank the DC3 co-principal investigators and the team that really made DC3 work together, both scientifically and logistically. In particular, for this talk, I want to point out and thank Megan Vila and Alan Freed for their contributions in looking at convective transport of soluble trace gases. So we've been looking at the effects of clouds on tropospheric composition really over the last several decades. A lot of studies were done in the 1980s and 1990s to look at acid rain, and during that time period we identified the importance of aqueous-phase chemistry in producing sulfate. Soon afterwards, it was really pointed out how sulfate aerosols played an important role in climate, and so we all hurriedly put sulfur chemistry into our climate models, and we were included among those. In our studies, we learned how much the aqueous-phase chemistry contributed to sulfate aerosols versus the gas-phase chemistry. And what we found in our global models is that at least half of the sulfate aerosols out there is coming from aqueous-phase chemistry. You might ask what happens to some of the rest of that's produced in aqueous phase, and it gets rained out. So that's what's shown in this schematic here, the processes that are included in creating acidic rain in terms of emissions, transporting chemistry, and getting into clouds and getting rained out. But not only is sulfur affected by clouds, but other trace gases and aerosols are affected by clouds as well. Ozone concentrations are found to be reduced by about 10% or less, and our work showed that there was equal contributions of that reduction from both cloud chemistry, gas and aqueous phase chemistry going on inside the clouds, and cloud scattering effects. Thunderstorms are kind of a different beast. They're really these complicated, fun, exciting storms to look at, and so I want to focus my talk on that. And so what I'm going to do is begin by giving a 2-page introduction to the deep convective clouds and chemistry field campaign, and then discuss some of the motivating questions we had before we went out into the field. And then I'll tell you about some of the things that we learned from the DC3 measurements, and then finish with some future directions. So the Deep Convective Clouds and Chemistry Field campaign was led by myself, Chris Cantrell, Steve Rutledge. Bill Brune, Jim Crawford, and Heidi Hintruser. You can tell by our affiliations that it was a collaborative effort between NCAR, the universities, NASA, and the German Space Agency. So it was a really nice effort put together by these different communities. We had two major goals in the DC3 field campaign. The first one was to characterize thunderstorms and how they process chemical compounds that are ingested into the storm. So that means we're really looking at the convective transport, the lightning that's going on in these storms, and then the production of nitrogen oxides from that lightning, as well as the chemistry occurring in and near the storms. The second objective of the field campaign was to quantify the changes in the chemistry and composition in the upper troposphere downwind of active convection. And what we really wanted to go after was finding out more about the production of ozone in the upper troposphere, where ozone is a radiatively active gas. And just to emphasize the importance of ozone in the upper troposphere, there were a number of modeling studies in the early 2000s that simulated this high ozone in the upper tropospheric summertime, and then a paper by Owen Cooper and colleagues that showed observations that this high ozone really did exist in the over the southern US in the upper troposphere. And this is an example from Owen's paper that shows an interpolation of ozone sonde data with this bullseye of high ozone over the southeast US in August of 2006. They estimated that that ozone has a radiative effect of about 0.5 watt per meter squared, which is fairly substantial, but also remember that this is a regional effect for a roughly a month-long time period. So one of the questions is where is that high ozone coming from? Cooper and his colleagues hypothesized that that high ozone is from chemical production in convective outflow regions. So I want to take a moment for our Atmospheric Chemistry 101 lesson about how we make ozone. Ozone is coming from nitrogen dioxide when it gets photodissociated, so you need nitrogen oxides and sunlight to make ozone. But ozone and NO react and make NO2, so that's not really making ozone. What we need is a lot more chemistry going on, and in particular, we need to have volatile organic compounds, species like carbon monoxide and methane, that will oxidize to form these peroxy radicals that then go on to produce NO2 and then make ozone. So the key things I want you to remember is that we need sunlight, we need nitrogen oxides, and we need hydrogen to create ozone. I also want to point out 3 particular species that I'm going to be talking about, and that includes hydrogen peroxide, methyl hydrogen peroxide, and formaldehyde. And these species are really interesting because they have an intermediate lifetime. They'll last for hours to days in time, which means they get transported away from their emission source. But they're also soluble and will react in the aqueous-phase. And so they are very interesting to look at in terms of what happens to them in thunderstorms or in clouds in general. So our questions from this chemistry is learning how much ozone is produced in the upper troposphere convective outflow regions. Previous studies, primarily modeling studies, have estimated that ozone production is about 4 to 15 parts per billion of ozone produced per day. And that depends on the amount of NOx and the amount of VOCs that are getting into those convective outflow regions. There have been some measurement studies aggregating data to try to estimate this ozone production as well, given a similar number, but there have not been any direct measurements of chemical aging from near a storm to downwind. So one of the things that was addressed in the upper tropospheric ozone question is estimating how much ozone is made in downwind of this convection. But I wanted to point out to a study that I led to try to understand what's going on with thunderstorms in chemistry. One of the challenges is the fact that we need to try to represent the convection at these small scales that convection acts at on just a few kilometers over a large region, because we're affecting this really large region in the southern US. And what I should point out here is what I'm showing here is a prediction of ozone at 250 hectopascals for 1 times point in this model simulation. What's shown in color is ozone, and what's shown in the black lines are these geopotential heights. So what's depicted here is an anticyclone during this time period. This WRF-CAM simulation was done at convective permitting resolution, so at 4-kilometer grid spacing over the entire continental US, and was integrated over a several-week time period. And what these things are showing you is all the structure that's in ozone over this 250 millibar region. You see regions of low ozone as well as high regions of high concentrations. And really what's interesting are these filaments. And you can see from a tracer of stratospheric air that many of those filaments are related to the stratosphere. On the other hand, there are also regions of high ozone that have signatures of boundary layer air, suggesting that ozone is being made in situ from these convective outflow regions. And often these things are happening side by side. And one kind of quick look here is that you see some fresh boundary layer air here, right next to some of the stratospheric air coming in. In addition, there's some stratospheric air that looks like it's getting mixed in that's from the thunderstorms themselves. So one of the conclusions that we had from this paper is that the high ozone in the upper troposphere is likely a combination of in situ chemical production and stratospheric air. And there have been some evidence of stratospheric air coming into the upper troposphere alongside these thunderstorms. I cite a couple of references in this first line, and here's an example of what the Dye et al. Paper reported from an objective analysis that Bill Skamarok led of the stereo storm, the 10th of July stereo storm. Stereo is a thunderstorm project that we had back in 1996 in northeast Colorado. And what's shown here for ozone, which is showing the ozone concentrations across the anvil region. So here's the cloud anvil of this particular storm. We see that there's low ozone being transported from below to the middle of the convective outflow region. But we see this high anvil, high ozone near the top edge and along the side of the anvil. And similarly, in carbon monoxide, we see very low carbon monoxide concentrations, again indicating stratospheric air. So it's showing an indication that there's some mixing happening between the upper troposphere and the lower stratosphere. In addition to stratospheric air coming into the upper troposphere, we also have seen evidence of overshooting plumes from thunderstorms entering the lower stratosphere, which is hugely important for water vapor getting into the lower stratosphere, being an important radiative effect as well. So one of the questions from this type of evidence is asking how frequently do we see mixing between the upper troposphere and the lower stratosphere associated with thunderstorms. So now I want to talk a little more about thunderstorms and all the different things they can do to the composition of the troposphere. There's transport and there's chemistry going on. And more importantly, there's things like production of nitrogen oxides from lightning and scavenging of some of our trace gases and aerosols. To simplify things, I'm going to focus on convective transport and production of nitrogen oxides from lightning. One of the things I wanted to point out in terms of the convective transport is shown here, that we're moving things from the lowest couple of kilometers of the atmosphere to the region of the upper troposphere that covers a little bit broader depth of 5 or so kilometers, but also the transport times it takes to go from cloud base to cloud top. And so an analysis, again, that Bill Skamarok led, showed that it took about 10 to 15 minutes to go from cloud base to cloud top. And then when I looked at those same trajectories and looked at how long those trajectories were in contact with the aqueous phase with liquid, it only took about 10 minutes of time. So aqueous phase chemistry only has about 10 minutes to get cranking along and doing something to the composition. One of the questions that we might have is how well do we understand the convective transport, and maybe we can assess that with cloud modeling studies. And so shown here is a cloud modeling inner comparison of chemistry transport models. So we're doing this at a resolve scale, cloud resolve scale, where we're simulating that storm, 10th of July storm from stereo, and we're comparing how well different models are in predicting the carbon monoxide and ozone, which are both passive insoluble species, and comparing how well we can predict them in the convective outflow region. So again, this is going across, the flight track going across the anvil. We see CO increasing in the middle of the anvil, and alongside of all these different colors from different models is the black line of observations, which is really hard to see, which tells us that we're doing a pretty good job of predicting the convective transport. And that's a similar answer for ozone, except for this region along the side of the anvil where we have stratospheric air coming into the upper troposphere. So this gives me confidence in how our cloud resolving chemistry transport modeling represents convective transport, and also means that it's really, these species like carbon monoxide, hydrocarbons, are all excellent trace gases for analysis of other aspects of thunderstorms and chemistry. What about soluble trace gases? Here's that same intercomparison between different cloud models, but now we're comparing formaldehyde and hydrogen peroxide. And now we see this big difference between the different models. Some think there's going to be a lot of formaldehyde coming out. Other models think there's not going to be very much formaldehyde coming out. And similarly for hydrogen peroxide. What you don't see on this picture from our 1996 field campaign are observations of these two species. And that's because that we were not measuring those species in the upper troposphere in these convective outflow regions. So that was something that we were dearly lacking at that point. And then I wanted to talk a little bit about one of the possible reasons for the differences from the different models. And I think that could be due to the cloud physics that's going on. And one of the big processes in cloud physics, especially in thunderstorms, is the briming process. So when snowflakes and graupel and hail fall through a population of cloud drops, they collect those cloud drops, and those drops freeze. And when those cloud drops freeze, you might ask, those trace gases that are dissolved in the cloud drops, do they also get caught up in those frozen particles, or do they degas and go back to the gas phase? Or is it a little bit of each? And so just to look at so we looked at some of the bounds of that, of what would be the implication if the dissolved trace gas was completely frozen, and it means that it would get caught up into the precipitation and get rained out, versus getting degassed, which means it would continue on up in the updraft region and go out into the upper troposphere. So it would make a big difference, suggesting that these models that might have predicted complete retention were removing the soluble trace gas in precipitation, and others that were assuming that these species were getting degassed would be going on up to the upper troposphere. So that's a question that we have about how much these aldehydes and peroxides are being lofted versus being rained out, and how much these aldehydes and peroxides are being retained in the freezing drops. So now I want to switch to talk a little bit about lightning and its production of nitric oxide. So as many of you know, when lightning is triggered, the temperatures increase. That heat splits up the molecules, including the nitrogen and oxygen molecules, which then recombine and start forming nitric oxide, as shown here in these reactions here. I'm going to take this from a little bit of a modeling perspective in trying to represent what's going on and determining how much NOx is produced from lightning. So in order to do that, we need to know a few things. One is the lightning flash rate. Another is whether it's a cloud to ground or an intracloud flash. A third is how much NO is produced per flash. And then the fourth is where do we put that NO source, both vertically and horizontally in these storms. So I'm going to begin with asking how do we predict lightning flash rates? Well, we could go all out and predict the charge in these thunderstorms and have those charges trigger lightning. That's rather a intensive computation to do. So there have been a lot of parameterizations developed based on different storm parameters. Commonly used is the cloud top height, but these other storm parameters have also been tested to predict lightning flash rate. And I wanted to show you that one of the challenges of using these storm parameters is actually being able to model them properly. And this is just an example from a study that we did a few years ago that's showing observations of these parameters, such as the updraft volume, compared to the model predicted updraft volume. And secondly, compared to the maximum vertical velocity, and then also to the cloud top height. And what you see from these plots is that sometimes they're doing a pretty good job and sometimes they're not doing that great of a job. So one of the challenges is predicting those storm properties. Another challenge is having the data from lots of storms to improve the statistics in developing these parameterizations, connecting the storm parameters to the lightning flash rates. So one of our questions at this point is, can we predict lightning flashes better? And then taking those lightning flash rates, we can then move on to trying to predict the production of nitrogen oxides for the lightning. And so there have been several studies that have been looking at how much NOx is in these convective outflow regions. There are several aircraft measurements, studies done in the 1990s and 2000s that really show an abundance of nitric oxide in the convective outflow regions. There are estimates made that on the global scale that lightning NOx emissions are anywhere from 2 to 8 teragrams of nitrogen per year. And that range is mostly caused by a lack of knowledge of how much NOx is produced per flash. And so that's what's shown here from several studies. Shown here on the x-axis is publication date of a number of studies. And then on the y-axis is the production rate of NOx from lightning in moles of NO per flash. And so early on, there was some theory and laboratory studies showing anywhere from 100 moles of NO to 1,000 moles of NO per flash. And then these aircraft measurement campaigns came in, and we tended to start seeing, getting estimates of around 400 to 500 moles of NO per flash, mostly in mid-latitude storms, and 150, 200 moles of NO per flash in the tropical storms. Suggestions of why there is a difference between the mid-latitudes and tropics is likely due to the length of the lightning flash, where there's a connection between the wind shear with the higher wind shear in the mid-latitudes compared to the tropics, suggesting that there might be longer flashes in the mid-latitudes compared to the tropics. So with this range, with these uncertainties that we see, one of our questions is, can we reduce the uncertainty in the lightning NOx production? So for those of you who've been taking notes, these are the questions that we've come up with. How frequently do we see the mixing between the ET and LS? How do we see direct evidence of ozone production in convective outflow regions? What's happening with these soluble trace gases? Are they being lofted, or are they getting rained out, or somewhere in between? And then can we predict lightning flashes better and reduce the uncertainty in lightning NOx production? And that led to the DC3 field experiment. And the way that we did that in this experiment was take advantage of a variety of facilities. We had ground-based radars and lightning mapping arrays that characterized the storm in terms of its kinematics and structure and the lightning activity. And then we had weather balloons that were launched in the environment of the storms to characterize the storm environment. There are 3 aircraft involved in the DC3 field campaign: the NASA DC-8, the DLR Falcon, and the NCARD Gulfstream 5 aircraft. And as you can tell from this schematic, we placed these planes in different regions. And one of the unique things that we did was that we coordinated the flights between the DC-8 and the Gulfstream 5 aircraft. And so both aircraft would fly out to the same storm. The DC-8 would go fly in the inflow region, and then the Gulfstream 5 would fly in the outflow region. Lastly, in order to make this field campaign successful, we needed just to have very good weather forecasting, and we were lucky enough to have some excellent forecasts during that whole time period. DC3 took place in Salina, Kansas. That was our operations base. But we flew to thunderstorms in northeast Colorado, western Texas to central Oklahoma, and northern Alabama. And the reason we chose those 3 sampling sites was mostly to improve our chance of sampling storms. We were really worried that drought might show up and we wouldn't have any storms to sample. So we improved our chances to sample storms. That also gave us the opportunity to have a variety of storms to look at, and also a variety of chemical environments. And then all these 3 locations were chosen because they all had very good ground facilities in the area. Just to give you an example of our correlated aircraft sampling between the G5 and the NASA DC-8, I'm going to show you just a couple of flight tracks of these for the May 29th northern Oklahoma storm. And a picture of that is shown here. Is a severe storm that occurred that created 5-inch size hailstones. So it was a very strong storm. This is showing the flight patterns for both the DC-8 and the G5. The G5 is in white and the DC-8 is in black. And what these planes did was we flew out early. We were out in the region before the storms developed. Once they initiated, we sent the airplanes to their respective sampling regions. So here is an example of the DC-8 flying in the inflow legs. Here's an example of the G5 flying in the outflow region. 2 hours later, the storm developed further. And in that 2-hour period, the DC-8 finished sampling the boundary layer. It spiraled up and also is now flying in the outflow region. So we have both airplanes in the outflow region characterizing what was coming out of this storm. So we now have over 25 papers describing results from the DC3 field campaign. Those papers cover things from the field program itself to new instrumentation being described. We have a few papers describing mixing between the upper troposphere and the lower stratosphere. These papers that I've highlighted in yellow, I'm going to show a highlight from in a few minutes. We also have papers discussing the lightning characteristics from DC3 in the different sampling regions, and also the production of NOx from lightning. Those are recent papers that either have been submitted or just accepted. I'm going to spend a little bit of time talking about convective transport of the peroxides and formaldehyde, but there have also been studies looking at the aerosol convective transport as well. There have been a couple studies looking at chemistry in the upper troposphere, and then some studies looking at cloud physics of some of the storms, as well as the aerosol distributions of brown carbon. So I'm going to begin with the Stratosphere-Troposphere exchange associated with storms, and I think this is one of those best examples of Stratosphere-Troposphere exchange from these aircraft observations. What's shown here is a satellite and radar image of a mesoscale convective system over Kansas, and the DC-8 aircraft returning back to Salina from the eastern US. And the DC-8 had a LiDAR on board, an ozone LiDAR, and that's what's shown in the lower panel for this section here. And so this LiDAR is showing ozone, high values in the stratosphere above the airplane. Here are the in situ ozone measurements taken aboard the airplane, also in the stratosphere. We see low ozone concentrations in the lower troposphere. And then in the upper troposphere, you see a lot of interesting structure. And really the premier structure to see is this high ozone concentration wrapped around the anvil of the storm, which is in black here, as this airplane started flying over the anvil of the mesoscale convective system. So, but not only is there high ozone there, you can see high ozone coming down in filaments from the stratosphere and other parts of the upper troposphere. So this is really a fantastic example of exchange, of mixing between the UT and LS. There's been a lot of work looking at the lightning flash rates. And there have been, one of the big efforts has been coming up with new flash rate parameterizations or refining the flash rate parameterizations that have already been developed. And we're now in the process of testing these new flash rate parameterizations in our models like WRF-Chem. One of the things that Eric Bruning has been spearheading is this new method of getting the size of the flashes. And that's kind of shown here in a schematic where you can create a polygon around these lightning flashes and then estimate what the size, what the area of that flash is. And the reason I want to bring that up is that that information can be applied to our studies on lightning NOx production. And that's what I want to present. Here is this estimate of lightning NOx that Ilana Pollock led, where we wanted to first and foremost figure out how much lightning NOx is being produced in the DC3 storms, but also look at how that production compares to different parameters. So here's the plot that I showed you earlier in terms of how much NOx is produced per lightning flash. And I added in the results from our paper showing that in DC3, on average, the lightning NOx production was around 200 moles of NO per flash, which is actually fairly different from some of these other studies and more like the tropics. And so answering the question of can we reduce the uncertainty of lightning NOx production, I think the answer is probably no, but there may be a correspondence between lightning NOx and the flash area, or lightning NOx and the low-level vertical wind shear. And I want to show the results of the five storms that were analyzed for the production of NOx from each of these storms versus the flash area estimated from each of these storms. And you can see that for all but one of the storms, that there definitely is an increase of NOx production per flash compared to as the flash area increased. And that there might be a connection to the low-level vertical wind shear. Again, as vertical wind shear increase, there's a little bit more NOx being produced. So the statistics aren't great, and there are only 5 storms to look at, but it gives us a lead as to maybe a path forward in predicting lightning NOx better. And now I want to start looking more at convective transport and scavenging. I want to remind you of the chemistry that's going on, that we're going to look at formaldehyde and the peroxides, which are soluble trace gases, that they're an important component of the precursors that make Hox radicals and ozone. And so we're interested in how much went into these storms, how much is coming out, in order to understand the chemistry going on downwind. These 3 species are very interesting. We have hydrogen peroxide, which is very soluble, so we expect it to get rained out. We have formaldehyde, which is moderately soluble, and methyl hydrogen peroxide that's mildly soluble, something that you expect to get transported up and into the upper troposphere. The way we did this is work that I led with the peroxides and Alan Freed led with the formaldehyde. The way that we did this was to first determine the entrainment rate into the storm, and then use that entrainment rate to determine how much of the peroxides could have been transported to the top of the storm if they had not dissolved into the cloud droplets. And then from comparing that answer to what was actually measured, we can get after the scavenging efficiency. To sort of emphasize that, here's the entrainment rate equation, where I'm using VOC, volatile organic compound, to be a passive tracer to help us determine the entrainment rate. And basically what we're saying is that the volatile organic compound at any point is a combination of what comes up from below and what gets entrained into the storm. And so we use butanes and pentanes for our volatile organic compounds and do an iterative process to get that entrainment rate. Once we know the entrainment rate, we can do the same equation for our peroxides or our formaldehyde and get their values at the top of the storm, which we then compare to what was actually measured. I looked at 6 storms, 4 of those in northeast Colorado and southwest Nebraska, and 2 of them in northern Oklahoma. And here are the results that we found for those 6 storms. So I'm showing all the results that I came up with my peroxide studies. Alan looked at 3 of these storms, and so I listed those results as well. And so we can see with the formaldehyde that we have fairly consistent results, ranging from about 40% to 50% scavenging efficiency from the observations. This compares in the same range from previous studies, which range anywhere from 11 to 57% scavenging efficiencies. We see that hydrogen peroxide is quite soluble and is getting removed. Its scavenging efficiencies are 80% or greater. Methyl hydrogen peroxide has produced something that was quite interesting. The range of results are from 12% to 84%. And that's quite different from what we expected, which was 7% or less. So that's kind of interesting. But the other thing I want to point out is that we have some really large uncertainties with these results. And that's due to uncertainties in the peroxide measurements themselves. But nevertheless, all these numbers are above what we expected, and several of these numbers are, minus their uncertainty, are still greater, producing scavenging efficiencies greater than we expected. So my question is, why would this less soluble methyl hydrogen peroxide have scavenging efficiencies nearly as high as the soluble hydrogen peroxide? And so I kind of went on a little investigation to try to figure that out. And I looked at several attributes of these storms, ranging from the chemistry to the storm environment to the cloud physics. And I'm going to step through a little bit of that over the next couple minutes. Just to look at a little bit of the chemistry, the methyl hydrogen peroxide shown here is being produced from this methyl peroxy radical, which is also reacting with nitric oxide to form formaldehyde and nitrogen dioxide. And the question is if you add lightning knocks to the system like you do in a thunderstorm, are we directing more of this methyl peroxy radical down this pathway instead of the methyl hydrogen peroxide? And the answer is yes, I think we are, but I don't think we're doing enough of it to cause such a big discrepancy or big variation in scavenging efficiencies among the storms. Another thing that's going on in these storms is aqueous-phase chemistry. And I looked a little bit at the aqueous-phase chemistry of methyl hydrogen peroxide in my 2007 paper, and really didn't see any effect of the aqueous-phase chemistry on methyl hydrogen peroxide. But I didn't include this one reaction. And so I really wanted to make sure that that wasn't what was causing this variation in the methyl hydrogen peroxide scavenging efficiencies. And so what I did was I compared our scavenging efficiencies to the inflow SO2 concentrations. And what you would expect is if you had more SO2, you would have more scavenging of methyl hydrogen peroxide. And what we find is the opposite effect. So it doesn't look like this is causing the big variation of scavenging efficiencies for methyl hydrogen peroxide. So just going back to my list of possibilities, it looks like chemistry is probably not the main reason for methyl hydrogen peroxide scavenging to vary so much. So let's look a little bit at the storm environment. And I'm going to talk about the intensity of the storm in terms of the convective available potential energy and the low-level wind shear. And then I'm going to talk about entrainment. So if you plot the scavenging efficiencies in the CAPE low-level vertical wind shear parameter space, you can see by the size of the dots, which are scaled by the amount of scavenging, that there's really no correlation going on between the intensity of the storm and the scavenging of methyl hydrogen peroxide. However, I would say that the two greatest scavenging efficiencies are in two very severe storms. I also looked at the depth of the liquid water region. That's the cloud base to where the temperature is minus 40 degrees. And there was no correlation with that depth of the storm. So the other thing I wanted to look at was the entrainment rate, because I noticed how much the entrainment rate varied among these different storms. And what I did find is that there is a moderate correlation between the entrainment rate and the scavenging efficiency. So that means that we're entraining in lower mixing ratios in the free troposphere into our storm, making it look like there's more removal of methyl hydrogen peroxide with higher entrainment rates than at the lower entrainment rates. So that suggests that entrainment of the background environment is potentially important to these scavenging efficiencies, but that correlation wasn't strong enough to say that's the only reason for causing the variation in scavenging efficiencies. So let's look a little bit more at the cloud physics. And I'm going to do that first by using some WarpChem simulations that Megan Bila conducted. And she looked at the 29th of May severe storm that I showed you earlier. And this plot here is just showing you that the observations and the model simulation are showing fairly similar storms in terms of the size of the storms being predicted. This is for early on in the storm lifetime, and this is for later in the storm lifetime. And so we have similarities in the size and the radar reflectivity intensity for the storm. So we think we have a pretty good representation of the storm. And we were really interested in this retention of the soluble trace gases in frozen particles. And so so we ran the cloud resolving simulations for a variety of conditions where we looked at retention factors ranging from 1 to 0. And what we've learned from this is a few things. So here I'm showing the observations of the scavenging efficiencies that were derived from both my study and Alan's study, and then the results from the WarpChem model simulations that were derived from Megan's model simulations. And we can see that hydrogen peroxide is getting removed, similar to what we learned in the observations, and that the formaldehyde has similar scavenging efficiencies when we assume that there's no retention of formaldehyde into these frozen particles. The methyl hydrogen peroxide is doing something very interesting. You can see that it changes. The amount of scavenging changes depending on how much of the methyl hydrogen peroxide is retained in the frozen particles or not. So that's, I think, a very interesting result and suggests that the ice is playing a role in methyl hydrogen peroxide scavenging. I think the other thing I want to point out is that the model is also predicting scavenging efficiencies much larger than we expected, of that 10% or less. So just to follow up a little bit more about Grapple and Hill, I was curious if we could see something in the observations. And the one way that I thought I could do this was looking to see if there's a connection between the size of the Grapple or Hill region with the scavenging efficiency. And so what I'm actually using is the radar reflectivity volume that's greater than 35 dBz, using that criterion as a way to represent the Grapple and Hill region. And so that's what's shown here is actually the volume per storm, 35 dBz volume per storm core, compared to the scavenging efficiency. And we get this mild correlation of seeing that it's when we have a bigger Grapple or Hill region, a bigger 35 dBz region, that we do get a greater scavenging efficiency. So that suggests that this is also a potentially important part of explaining the variation of the scavenging efficiencies for methyl hydrogen peroxide. So none of these is one direct reason of saying what's causing the variation, but these do provide guidance for further analysis, especially when using cloud chemistry models. And that takes us to, again, why is this important? Trying to understand how much of the formaldehyde and the peroxides are getting to the upper troposphere. And that's because of the chemistry that's going on. And I wanted to show you one highlight from the DC3 field campaign of trying to get some direct evidence of ozone production. And that's this case that we had on the 21st of June in 2012. And what we came up with this idea of was looking in the convective outflow region of a dissipating mesoscale convective system. So here you can see that MCS over the Missouri region. And what we did is we flew the airplanes one after the other. So first the DC-8 went up early in the morning and started flying in the convective outflow. And it tried to stay in that same convective outflow air for the next several hours. The G5 came out and joined it and took over for the afternoon, again, trying to stay in that same convective outflow air. And so our preliminary results show for ozone that we had very low concentrations in the morning of about 50 parts per billion, and then that increased significantly in the middle to the later part of the afternoon, where it reached values of 70 parts per billion. So 15, 20 part per billion increase of ozone. So this is tantalizing, but does need further analysis to definitively say what's going on. So just to recap, what we learned from DC3 is that we did find lots of evidence of mixing between the upper troposphere and lower stratosphere in and near the thunderstorms. We have used the data from the DC3 field campaigns to come up with better, hopefully improved parameterizations of lightning flash rates. And although we may not be able to improve our uncertainty in the lightning NOx production, we think that there might be pathways forward by using other parameters like the size of a lightning flash to help us predict the production of NOx from lightning. The convective transport of soluble trace gases has been examined, and we see kind of this highly soluble hydrogen peroxide being scavenged, formaldehyde having about half of it being scavenged, and methyl hydrogen peroxide showing this interesting wide range of scavenging efficiencies. The second question was whether these are being retained in the freezing drops, and we actually seemed to get different answers where it didn't appear that the retention was necessary for formaldehyde, and maybe not for hydrogen peroxide either. But it looked like it might be important for methyl hydrogen peroxide. And then lastly, we have this one case where we think we have some really nice evidence of ozone production in the convective outflow region. And so now that takes me to wanting to present a couple of future directions to go with thunderstorms in chemistry. And I want to kind of go back to one of the things I said early on in the presentation, and that's understanding the impact of thunderstorms on the regional scale, and which is a really kind of challenging thing to do. And I don't think that we should just look at what's going on in the US, but I think there's some other really interesting regions in the world. In particular, I think the Asian summer monsoon region is very interesting because of the vastly different polluted conditions compared to the central US. And that brings up interest in looking at other processes, such as how important are aerosols in affecting the storm dynamics, the physics, and lightning and subsequent chemistry. And if you remember, I said that there's this challenge of being able to represent these convective scale processes over a large region. And in that simulation that I showed you really was a challenge to do. And so I'm thinking now that maybe using the model for prediction across scales with chemistry is a good way forward to do these types of studies. The second future direction is to focus back onto the aqueous-phase chemistry. So we know the aqueous-phase chemistry is important for sulfur and producing sulfate aerosols. I think it might have a fair bit of importance for organic chemistry. Many of you are familiar with this Zhang et al. Paper that showed the composition of aerosols through a variety of places across the world. And we see that, yes, sulfate's an important part of it, but organic aerosols are also a very important part of the aerosol. And so you can take this schematic of the sulfur chemistry and just overlay it with the organics, and we have really the same basic idea of where we have the emissions of these organic compounds. They're transported and undergo chemistry, making oxygenated VOCs that then get dissolved into the cloud droplets and undergo aqueous-phase chemistry. And the question is how important is that aqueous-phase chemistry to the production of organic aerosols? There have been some laboratory model studies that suggest that it does play a fairly important role, but I have not yet seen evidence from the field showing aqueous-phase production of organic aerosols is happening in these clouds. And so I suggest that maybe starting with some mountaintop clouds, such as in the observatory at White-Faced Mountain in New York, maybe looking at some small cumulus clouds where you have just liquid water, so you can look at what's going in and what's coming out at the top. And so we're trying to move forward with this with a workshop later this year that I'm helping to co-organize to start designing an experiment to look at this aqueous-phase chemistry. Along with the getting direct evidence in the field, I think we need to continue to improve our representation of the aqueous-phase chemistry in our state-of-the-art models. And so with that, I'm just going to list what points I tried to make during my talk about thunderstorms and their effect on the composition of the troposphere, what we learned from DC3 in terms of transport and lightning and chemistry, and then remind you of these future directions that I just mentioned. And I'd like to thank you for your attention.
Thanks, Mary. Questions? And this is being recorded, so please wait for me to get to you with the microphone. Questions?
Thanks, Mary. In terms of the lightning produced NOx and the new study with the DC3 campaign, did you imply that there was a difference in how you calculated the lightning flash duration and or sizes, and that is that the difference, or is it actually different physically?
So there were a couple of methods used to come up with this production of NOx that I didn't really mention, but one is based on, they're just two different approaches of either using the volume of the storm or using a flux through the anvil. But those points are quite close to each other. What we're showing here is an average flash area for each storm and the estimated production of NOx from that storm. So we don't have, and then we take that and divide by the number of lightning flashes that occurred. So that's how you get this NOx per flash.
And that's the same on the electric flow as well?
Yes. Yes. Is that good?
Same plot. I was wondering what's your hypothesis for this connection between low-level shear and lightning
I should explain that a little bit more. So it kind of came up when the Heidi Hooten-Reeser's papers started reporting these lower values of lightning NOx production from these tropical storms. And so she was the one who threw out this idea that in general in the tropics there's lower vertical wind shear than in the mid-latitudes. And her thought was, well, maybe the wind shear is actually playing a role in creating storms where lightning can be longer.
Thank you, Mary. Nice summary, nice project. You looked at the scavenging with respect to things like entrainment, but we know in DC3 there was a wide variation in the amount of water that was actually in the anvil. Have you looked at all in terms of things like precipitation efficiency?
Yeah, well, so using the same method for water, I come up with very high precipitation efficiencies. But I think I would argue, so I also looked at the scavenging efficiencies in terms of the ice water content measured in the outflow, and there's really no correlation. And I actually worry a little bit about that comparison because sometimes we're measuring the outflow 15 minutes away from the storm core. Sometimes we're measuring it 45 minutes away or an hour. And so that ice water content could be quite different depending on what distance you are from the storm core. So I'm a little bit worried about using it in that simple way. And I think maybe finding a more robust way to do it would be better.
Yeah, I just think we could look at, it's clear that some of the storms are much more efficient at removing water than others, but as it drifts downwind, it's going to be affected too. But that's another thing we could look at.
Mm-hmm.
Part of the operational plan of DC3 was to look at storms in very different regimes, from the high plains of Colorado to a more tropical Alabama. And the idea was maybe that the properties and the chemistry were different in these very different regimes. Were you able to document any differences in how things work from over the different regions?
So unfortunately not for the peroxides. I wanted to use a consistent measurement of the peroxides. And so I used the DC8 data from my studies, and And for our Alabama storms, the DC8 flew only in the, really only had inflow data, and so didn't have the outflow data. So I couldn't do that with the peroxide measurements. I think Alan tried to do it with the formaldehyde. He did find a very different scavenging efficiency, but he has concerns about that because we're not quite sure that the air that we sampled in the inflow region was connected to the outflow region. And we checked that by looking at ratios of hydrocarbons, so the iso and butane ratio in the inflow region. We wanted to have the same ratio in the outflow regions, saying that it was the same air moving from down low to up high. So hopefully that makes sense to you. But that's one of the tricks. And all these storms that I showed you here, we had good connection between the inflow region and the outflow region.
The pentanes too.
Yeah, we also use pentanes. So that's again, suggesting, if you trust your convective transport, you can use these hydrocarbons and carbon monoxide and other species to show where the transport's going.
Any other question?
Don's going to get after me in entrainment.
Yeah, it strikes me that entrainment must be a very hard thing to measure with the observations that you had. I wonder if you could say a little bit about how you did it, just in very rough terms, and how confident you are of how well you were able to measure it.
So we talked about entrainment before the field campaign went, and as many know, Don's in favor of let's do circles to get after entrainment rates. But you also saw that storm that we measured May 29th, and there's not a chance we would have gotten around that storm in a reasonable time. And so what we used instead were these passive tracers, the butanes and the pentanes. So we have 4 of them, the NNI butanes and the NNI pentanes. And they have high concentrations in the boundary layer, very low concentrations in the background free troposphere. And so providing a really nice strong contrast, which means there was also a strong contrast in the outflow region because those would be high values compared to the background region. And so there's some pluses and minuses, but this to me seems like a fairly good method to move forward in using these hydrocarbons to look at what kind of transport is going on. But there must be, you're right, we don't have another type of entrainment rate calculation to really show how well we did or not. Is that good enough for you, Don?
Any other question? Well, let's thank Mary again.